All right, well, now we're recording. Any questions?
I know it's maybe a little early, but does anybody else have any questions on the master set yet? No, not really.
Miraculously, I have no questions. None.
Did you have one, or?
Well, yeah, I have one that's probably decently self-made.
I have no questions.
So, for the fourth question on there,
All right,
I have it here.
that probably would be very helpful.
Well, I got different values each time, so I don't know if I'm doing something wrong or if it's supposed to be a different value for each.
Yeah, perhaps there's a different approach.
Okay.
What are you doing in the lab? How are you finding resistivity from the lab?
Well, that's due later than this, so I have not started.
Okay, fair enough.
We commend you for having started the master set.
Yes. All right, so ultimately you're going to be doing a graph, and it was resistance versus length, I believe, on the lab, and that's what they give you in the on that problem.
That's what, yeah, that's what it is here.
All right. What are the odds? So first off, what's the relationship between resistance and length? The ideal.
The longer it is, the more resistance there is.
Okay, and the formula?
R equals resistivity times area over length. I might have area and length backwards.
Yeah, length over area.
Yeah.
It's area. Isn't it area?
Ooh, it's contested.
The first thing that he said, the longer it is, should the resistance go up or down?
It should
Go
go
up.
Yeah, so therefore L has to be on
On
top.
Yeah, okay.
And also, think about if you're leaving a room, is there more resistance the narrower the door is or the larger the door is?
Smaller.
Smaller.
Right,
So as area goes down, resistance should go up.
yeah.
Or you could take a look at the units, but that's what we're working with here. So ideally, when there's no length, what is the resistance?
0.
Yeah, there's nothing inhibiting it. So in a nice ideal world, that's what the graph will look like. In reality, probably not. So what would cause it not to go through the origin?
Not having something 0?
Okay, that's,
So for the formula, the resistivity there, if you've got something if we're not going through something that has no resistivity, then it's gonna be moved up a little bit.
now if there is resistivity, I don't think that would move it, shift it up or down, that would cause it to tilt one way or the other. All right, so let's just drop back for a second. If I'm doing resistance versus length, what is the slope? What's the formula for the slope?
R over L.
Try the L's my X value and R is my Y value. So I see what you're going for. We can narrow it down better than that. Technically, if you're going that route, it's change in R over change in L.
I've always struggled with that with your labs.
Yeah, same.
Where you ask, like, based on everything you've just done, what is the slope?
Yeah, I'm with you, you know.
All right, so if you just do R over L. So let's take an extreme case. We've already talked about in the lab, it doesn't necessarily go, odds are going through 0. I think I've seen it once go through 0 without having it forced. Sometimes students pick the wrong trend line and they pick the one that forces it to go through the origin. So, not what I'm looking for here. So, let's say it looks like that. So obviously, we have some intercept. If, let's say it's based on these points line up perfectly, or at least close enough. If I just did R over L, going with what Brooke had said, basically what I'm doing is I'm finding that slope, and that slope. If I just do R divided by L, I'm finding the slope of each of those points that are going through the origin, which that doesn't. So the trend that you're looking for is one based upon the line itself and not the data points. But this fact that it's not zero, there could be an explanation. One could be zeroing. But in theory, it should be reading zero when you have nothing there. Well, actually, it's infinite resistance. When you touch the two leads, it should be zero. And so that's probably as good as we can get to it being zero, is the fact that it registers zero when you touch the probes. So let's take probably the second one. No, let's do the first one. So you had the wire board here, and you had your multimeter, and then you had the slider, whatever it was called.
Trolley.
Trolley. That was the word. I'm trying to remember what it was called. What you called it, at least. Then how did you measure resistance?
From the start, where the wire was at zero to wherever we touched on the trolley.
Right, and then we press down one side of the trolley to the wire to see what the resistivity would be. Because they would measure on the multimeter.
So what exactly were you measuring? I mean, resistance, yes. Resistance of what?
The
The wire, that little wire running across the yardstick.
What was the first thing you said?
The resistance for that, what resistance we're getting in between those 2 points on that little wire.
Where?
Yeah, like wherever the trolley is, when you press it down, we're just measuring the resistivity of that length of the wire.
Oh, so if I press that down, you're measuring the resistance of that?
Yes. Is that it?
Are you? Are you really?
Are we?
I thought so.
All right, so let's take the case of B and C. Let's take when you're doing 120 meters, you had the jumper, to the meter, and then that connected. What are you measuring the resistance of again?
I guess it would be the full length of the wire from the connection point in the multimeter to the other connection point going the long way, right?
Meaning, reword that, or say it again.
It seems like the length of the wire would include the wires that are connecting all of the other pieces.
Yep.
So we're measuring the resistance through the whole system, which begins and ends at the multimeter.
Yes. You're measuring the resistance between there. Now, we are making an assumption that the resistance of the probes, or those wires, the resistance here where you're attached to the metal, and the resistance of the trolley are all so small we can ignore it. And over here, yeah, we're measuring the resistance of all these other connections too. So there's a legitimate reason for it not to cross through zero, because we do have a bunch of other wires. And if you watch the video, I actually do look at the resistance of all the other wires. So the fact that it doesn't cross through zero could mean something, which is part of the answer to another question. Now, if you end up with a negative resistance, or sorry, negative intercept, you might have to think a little bit longer about what that means. But whenever you're trying to figure out the slope, which is where I was before, or what the slope should be, or again, the generic formula for a line. So this is slope-intercept form. Y is equal to slope x plus b. That's the slope, and that's the intercept, the vertical intercept. I guess y in the context of y, the r-intercept in the context of the graph right there. So I need to somehow get that into this form. Well, my y is r. My x is L. That's what I need to do, so it's R is equal to something times L. Well, what am I multiplying times L?
The rest of it.
The other two.
Okay. Brooke, it looked like you blanked on what that was called.
Yeah.
Okay, rho. Rho over A. And then plus 0. So ideally, the intercept should be 0, and my slope should be rho over A. Which will come in quite in handy later on when you try to find the resistivity. But, or if you have really nice data, which not for the lab, but might work on that problem over there, recognize that the slope delta R over delta L, it depends on how good the data is, whether that would work or not. And I don't remember how good I made the data.
It says it's 1.000000. That's not exactly.
Okay, so that would work also. Yeah, the trick on that one, originally, I think in an earlier version of it, I had it going through the origin, and that was just boring, because people just did R divided by L, and got an answer, and then I thought that, realistically, that's not gonna happen. Not that realism is necessarily a criteria for a problem to be on a test or quiz. Alright, I guess, Zach, you brought it up. Has it been answered?
I'm not sure. Something to think about for sure.
Okay.
Something
Do
to
you want me to
think
just
about.
move on, or do you want to mull it over for a second and then ask another question? All right, while he's thinking, anyone else with a question on this? All right, back to you, Zach.
I guess just the short question that I wanted the answer to is the idea that each of these different lengths of wire would be something different. That's not the case. They should all be the same thing. I have to figure out what thing that is.
Yes.
Okay. All right. Yeah, back at the drawing board then.
If you've done the lab, you can basically go through the similar steps, but this is outlined right here. All right, I'm gonna move on unless you want to follow up with something. Anyone else have a question on anything related to the climate force? All right, so we're going to start the first topic of post-test 1B. Magnetism. I am making the assumption that, and the assumption generally is played out well, that everyone in here has played with magnets at some point in your life. So what can you tell me about magnets?
I wanted to say opposites attract and like repels, but I can't explain. Like they're magnetized. I don't understand how that works, but I just know that they're the opposites attract.
All right. That's one thing that we know.
There's this one toy you could get at the fair. It's these two little magnets, and if you, I don't know Anybody knows what I'm talking about? You throw it up and they come together and then they would make a vibration.
I've heard them called rattlesnake eggs.
Yes, that's a good name for them. So we got some rattlesnake eggs going on with magnetism.
Which is related to the opposites attract like repels. I mean, they are attracted to each other, but then they hit and bounce a little bit, but then get sucked back together. And...
Yeah. Brooke kind of stole my thunder there.
All right, Brooke.
There's something called a magnetic field.
There is something called, okay. So,
Sorry for
there
stealing
exists.
that.
Don't let it happen again.
Don't let it happen again.
all right, the backwards capital E, that's just the shorthand for there exists. And this right here is the symbol for magnetic field. And I'm going to parenthetically put in here magnetic flux density. And then I'll explain that in a moment.
Do tectonic plates have to do with magnetism?
Say it again?
Tectonic plates.
Not to my knowledge. I can't make any real connection between tectonic plates and magnets, but that
Okay.
could just be, I've never had a geology course in
For some reason, I thought
geology,
they
and I
were,
was picked up for my wife.
I were related, but
There is the relation is they have, the thing that I know that they have in common is the tectonic plates are basically sitting on top of the plasma of the Earth's core, and the Earth's core is, the plasma of the Earth's core creates a magnetic field.
okay.
I think the evidence of Pangea is based on some of the magnetic leftovers,
Okay.
but I
Interesting.
could just be making that one up on the spot.
I'm gonna go with that.
Okay, there we go. So,
Yeah.
and for those throngs of geologists who are watching this, just write a polite note whether I was making stuff up or not.
Yeah, like your wife makes a burner account and just roasts you in the
I wouldn't put
comments.
it past her. All right, so when you say opposites attract like repels, what would be considered opposites with a magnet?
Plus and minus.
I'm gonna say no,
Oh.
and
Yeah.
I'm gonna.
Not Harrison.
Well, he was baiting that answer, and so I gave it to him.
Yes, that's exactly what he wanted.
That's exactly what he wanted from me.
Really, I was hoping someone would go for, like the Earth's got them too.
Like poles?
And what are the two types of poles?
Positive and negative.
Think of the Earth. What are the two types of poles?
North and
North
south.
and
North and south.
Oh,
That's what I was going
Fell
for.
for it again?
oh no, he's happy now.
Now, after having corrected Harrison, let me
Yes.
talk about how he could be right.
Just nothing I've said has ended up on the board, and it's kind of upsetting me.
I've been contributing quite a lot.
Snake eyes. Put the, no, not snake eyes, they're like,
Upsetting.
There we go.
There we go.
With charges, you have positive and negative charges. I could have a positive charge sitting in space. I could make something positively charged and have nothing else there. I wrap a Gaussian surface around it, and I know the electric flux going through that surface is equal to whatever that internal charge is divided by epsilon, or epsilon sub naught. Magnets have a north and south pole. Any magnet that you have, you'll have a north and a south. And again, I'm going to hesitate this. Any theorists watching this are going to probably, it's quite possible they'll go, yeah, he might be right, or no, I've wasted a lifetime of work. So far, we have only found north and south always going together. So I've got a magnet here. One side is north, the other side is south. Everything's fine and works fine like that. It is known as a dipole. Now, the question is, even though we haven't found it yet, does a north pole exist by itself, or a south pole exist by itself without the other one? There is a theoretical basis for it potentially exists, and my understanding of it is that there's still for every north a south pole, but you'll have a north pole here, and then there's some tenuous connection to a south pole that is very much removed that we would not see. So we could actually look at this and go, oh, yeah, there's a North Pole. And somewhere else, someone might be looking at it and go, oh, there's a South Pole here, not realizing that they go together. If this should show up, this is a magnetic monopole. And even though we haven't found it, doesn't mean the theorists haven't, laid it out of, hey, once you find it, here's the set of math equations. And in that math equations, they actually have sort of a magnetic charge, I think that's what they called it, using a lowercase m, because we don't use that enough, to represent it, in which case it might be a positive number or a negative number. So, plus minus might be valid, or it might not be.
North and south, it's kind of like the rule of two. If anyone is familiar with
I do know what the rule of two.
the rule of two. If you don't know, then you don't need to know.
Okay. Lead us.
Is that the every master has one apprentice?
Yes,
Yes.
the
Every
rule of
two.
Every Sith.
Now everybody knows.
It's all about the education.
Yeah.
All right, so when we're talking opposites attract, like repels north, south repels south, north and south like each other. Now, the magnetic field symbolized by the letter B. Now, almost every undergraduate textbook, they're going to be using the letter B for magnetic field. There are some textbooks that won't call that the magnetic field. They'll call that the magnetic flux density, and they'll use the letter H for magnetic field. And just to make it complicated, or simpler, this B right here, whether it's called the magnetic flux density or magnetic field, it's the exact same thing. Just that some textbooks decide that, you know what, this is really the magnetic field. They are related. We do not get into this, but if you might run across it at some point. Because we don't have magnetic charges, because we don't think about it in terms of a plus side and a minus side, we don't have a nice little Coulomb's constant, or Coulomb's law type formula for it. Here's the formula.